Okay, so Mr. Rice had that delightful video on discussing the Pivot Interactive stuff, trying to make sure we're doing all right, collecting some of that data. We're going to go through here and take a look at a brief bit of notes on some of the things that we've covered and some things along those lines. So I just have kind of a column of physics topics, description of the terms, and maybe what symbols we've used, and any units of measurement, like time is measured in seconds, distance in meters, things like them. A few things that I want to make sure we see. I'll just kind of highlight things here. So position is location from a reference point. We generally have to set a 0 spot, and then we measure position from that. And in the Pivot Interactives video, when we moved that ruler back and forth, moving that ruler back and forth was setting our 0 position where that reference point was, and then we measured position off of that. You can have positive or negative positions as well. We can say if this is 0, then maybe that way is negative, and maybe this way is positive. Velocity is how fast and what direction an object travels, both how fast and which way. It can go fast that way, it can go fast that way. Either the directions is significant. We'll do a little bit more careful description on this in a little bit, but here we see V is triangle D over triangle T. Well, that triangle means change in, or like distance 2, position 2 minus position 1, which kind of brings us back, if we've calculated slopes in earlier grades, that sounds a lot like y2 minus y1, x2 minus x1, and that kind of makes sense. It leads into this next thing. So velocity is how fast and what direction. If we're using it in an equation, the symbol would be v. If we're talking about general units of measurement, for us, we'll generally stick with meters per second, but velocity is also like miles per hour when you're in a car traveling down the road. So slope, the steepness of a graph. This is where in math we do a lot of stuff where we learn skills, but we don't always apply them immediately to things that have different meanings for us. In physics, we take these things and we do apply them. So the weird thing, the thing that's sometimes shocking to people new to this, is that the slope or the steepness of a line can have a meaning other than it's going up really fast. So when we talk about the slope of a position time graph, the slope of a distance time graph, the slope of a position time graph is the velocity of the object. Remember, the slope, you're talking about going so many distance, so many meters in so many seconds. That rise over run is your slope, and that slope is a velocity value if you're plotting position versus time. Now, different graphs, that slope will mean different things, but if you're plotting position versus time, that slope is the velocity. But what it is in every graph depends on what's being graphed. The y-intercept, that's the spot where the y-axis crosses, or pardon me, that's the spot where the graph crosses the y-axis, and again, that means different things on different graphs. We'll talk about it specifically relating to our ping pong ball cannon in a second. Generally, we use the little letter, the lowercase letter b, to describe y-intercept or to represent the y-intercept. And again, just like the slope in a graph has some like real life meaning for some thing that we can observe, the y-intercept also can have a real life meaning for this thing that we can observe. What it means depends on what we're graphing. XY scatter plots, that's just, there are a bunch of different ways you can graph things, right? You can do bar charts and different things like that. XY scatter plot is one of the ways that you know it's going to plot data points out correctly. A best fit or a trend line, people will call these different things: a trend line, a best fit line, a curve fit, all sorts of things. But really what we're saying is that it's a line that best matches all of our data points. We will almost never connect the dots for our data points. We're gonna, if we have a bunch of dots, we're gonna try to get the line that runs through a straight line or a consistent curve that runs through and represents all of our data the best. The independent variable, that's the variable that we manipulate or change or that we set, and we will then measure it, and something else will also change. But the independent variable is the one that we're able to control or set either through our physical nature of doing the lab, or like in the ping pong ball cannon, the time was the independent variable because the camera was set to take 2,600, I think it was, pictures every second. So time was every frame was 1/2,600th of a second. So that's a very short amount of time between each picture. If we wanted to change that, we could go into those camera settings. Well, we couldn't, but the guy that owns the camera, I know the guy, it is a guy, the guy that owns the camera, he could go and change the settings on it. So maybe it's not 2,600 frames per second, maybe it's 1,300 frames per second. So that gives us this variable that we can control and manipulate. And then when we control or manipulate the time at which we take a picture, well, then we can find what distance the object traveled, and that would make the distance or the position the dependent variable. That's the one that we observe how it changes depending on what we do with our independent variable. So that's the first bit of things right there. There's one more set of things to take a look at, and this is then taking a look at specifically the graphs that we collected or the data that we had, trying to make sense out of those equations. So we had a line that looked something like this. I mean, obviously the graph was a little bit different. It had green data points and that lime green line. Here I'm just saying position, time, and we have a straight line, right? So it's different levels of freshness in our brains depending on where we've been and what we've been doing. But the equation for every straight line everywhere is y equals mx plus b. So some of us, that might just roll off the tongue, easy peasy lemon squeezy. For some of us, that might not be obvious, but it is true. The general equation for every straight line is y equals mx plus b, where m is the steepness of the line or the slope, y is what you're plotting on the y-axis, what's going uppy downy, and x is what's going on the x-axis, the lefty-righty axis. B is the y-intercept. So that straight line equation, every equation for every straight line. Now pivot, instead of saying mx plus b, pivot used ax plus b. I don't know why, but they did. But so I have them both here side by side. Now our y-axis on our graph is position, or d, and the so down here y equals mx plus b, I put d instead of y. And our x-axis is time, so instead of x, I put t. So I just changed y to d, x to t, d equals the slope times the time plus the y-intercept. I did the same thing over here just to make sure that we see how it's reasonable for how these things go back and forth. Y to d for the position, x to t, and there we go. Now the slope represents the velocity of this graph. That's the big huge, like, that's the physics thing that we get from this lab. We get that the slope or the steepness of this graph tells us how fast we're going and which direction we're going. So the steeper that line is, then we're going super crazy fast. The more shallow that line is, the slower we're going. So if the slope represents velocity, now we can say d equals vt plus b. Did the same thing over here, just off of that y equals ax plus b column. Then the last thing is that the y-intercept, and the Pivot Interactives thing walks us through this. If we go through and reread the text in there, the y-intercept tells us the position or the distance of the object when time was 0. So if you remember on this graph, the y-intercept is where this blue line crosses the y-axis. And so when this blue line crosses the y-axis, time is 0, right? So when time is 0, what's the position? So the y-intercept, when this blue line crosses the y-axis, that is the position of the object when time is 0. So for this one, the position of the object, for this graph here, the position of the object when time is 0 is pretty much 0 the way this graph is drawn. It won't always be that, not for all types of motion. So then instead of saying B, we can sometimes say D with a little note down below, a subscript 0. Sometimes people think of that as D original. Sometimes people will say, no, I'm going to put a D1 down there for that's the first distance. But so now we have an equation for this motion. That's y equals mx plus b. But instead of y, we have d. Instead of x, we have t. The slope represents our velocity. The steepness of the line represents the velocity. And that y-intercept, where when the x-axis is 0, that is the original position, or the position that the object started at. So those are the sorts of things that we're trying to get from that stuff. 12 minutes, a little bit on the long side, but I think we got her. Take her easy. Have a good one. We'll catch you later. All right.